Hello everyone, welcome back to Engineering Mechanics. Our discussion will focus on vectors today. The concept of vector is very important for all engineers. You are going to repeatedly use the concept of vectors in solving various engineering problems. Some of you might have heard about vectors already in high school, and you might have heard definitions such as vector is a physical quantity that has magnitude and direction. Now, if that definition puzzled you, I want you to know the concept of vector is very simple and easy. In fact, believe it or not, you have been using the concept of vector in your everyday life. Let me give you an example. If you ever give a direction to someone to get to a place, and if you give directions along the lines that I'm going to say, for example, go forward, go in this direction, 100 feet, take a left, then go again forward for 20 or 30 feet. And the place that you are looking for is on your left. If you give such directions, you are using the concept of vector. You are telling someone how far to go, in which direction to go. That is actually dealing with vectors. Give you another example. Say you are driving from Los Angeles to Las Vegas. So you are driving west at 50 miles an hour in your car. If you say that you are driving towards west at 50 miles an hour, you are dealing with the concept of vector because you are giving a number related to the speed, such as 50 miles, and then you are also giving a direction. That's vector. Or if you play sports, you are kicking a soccer ball towards the goal, you are kicking at certain angle, and you are applying certain amount of force. That is dealing with vectors. Or you are shooting a basketball into a hoop. That means you are throwing a basketball at an angle and you are applying just the right amount of force so it can go into the hoop. You are dealing with vectors. All right? So vector is really a concept that includes two important parameters. One is a value, which I am going to use the word to describe as magnitude, which is actually a number. So a value, a magnitude, a number, a vector has that. As well as direction. Which way? East, west, maybe 30 degrees from the horizontal, maybe at an angle of 45 degrees. These two concepts come together, gives you vector. So vector is a more generic name. A force is a vector because you are applying certain amount of force, such as 50 pounds, 100 pounds along a direction. That's a vector. Or velocity is a vector, going in certain direction at certain speed. Acceleration is a vector. So there are many engineering concepts, engineering quantities that can be called a vector. So vector is an important concept that basically allows us to deal with many engineering quantities easily, and it allows us to help perform mathematical operations. So in the next few minutes, we are going to take a closer look at vectors, learn how to add them, subtract them, and deal with them in many different ways. So let's take a few examples. All right, everybody, let's take a closer look at vectors. We talked about vectors a while ago, and we know vectors are quantities, physical quantities that have magnitude and direction. As you know, magnitude is simply a number. It could be something like 10, 76, and so on. It is just a number. It's a value. A direction is, for example, going this way. In this case, it is going from, say, east to west. In fact, I gave you an example of going from, say, Los Angeles to Las Vegas, right? That would be going east at certain speed, which is like 50 miles an hour. That would be a vector. So any physical quantity, engineering quantity with magnitude and direction can be called a vector. What are the examples of vector? Well, we just talked about it, which is a position vector, right? Position with respect to something is a vector. A vector is typically denoted by an arrow at certain angle. So that's a position. Similarly, velocity acceleration. These are all examples of vectors. Well, there is one more example I want to spend a few more minutes. It is the force. All right, let's take a look at force vector. Force is an important concept, and we are going to be dealing with this concept all the time in statics. So let's take a force vector. Force, as all of you know, is a push or pull. It's like pushing something or pulling something. If it is push or pull, it has certain direction, right? I am pulling it this way or I am pushing it this way. So force has direction. Plus, we also apply certain amount of force. If you are using American system, you may say, I am applying 50-pound force. Or you may be using metric system, you may say, I'm going to spend or I'm going to exert 100 Newton force. So force has certain amount, which is the value, magnitude, and the direction. So force is a vector. Now, we have an understanding of what a vector is. Vector is a quantity with direction and magnitude. Now the next question is, how do we represent the vector? How do we show a vector? Well, let's take a look at this way. We want to show a vector using an arrow. This indicates which way, the sense is this way. And also it makes an angle in this particular case from the horizontal, say angle theta. So if I want to denote a vector, typically you will have to show some kind of an angle as well as the direction. And to write this down, let's say this is a force vector. I'm going to put a little dash on top of it. In books, you may find a bold letter for vector indicating it is not just an F, it is vector F. So vector F can be written like this. And it may be equal to, for example, 50 pounds magnitude, making certain angle along the horizontal, from the horizontal, in this case theta. Now, typically in engineering, we measure the angle from the x-axis, from the horizontal. So this is a conventional way of providing the vector's magnitude and direction. All right? There are other ways of representing. For now, let's stick to this. So anytime you are dealing with a vector, your answer must include two parts. One is the magnitude, in this particular case 50 pounds, as well as the direction it makes with a horizontal or an x-axis in this case. Also, the sense should be shown properly with an arrow. All right, if you miss an arrow, it is not a vector. In engineering, we want to speak a common language across the world. It doesn't matter what language you speak. If you represent a vector, people from different countries speaking different languages will understand. So it's very important you follow the notations. So this is the vector notation, and please follow this and do not ignore any one of those parts. All right? So now that we know how to represent a vector, we know what a vector is, the next topic is on how can we manipulate these vectors. And why do we have to do that? Think about it. You are applying some force. Say you want to pull something. It is too heavy for you to pull in, so you ask someone else to help. So let's say you have this big furniture. Two of us are pulling. We tie a rope, I pull this way, the other person pulls that way. So each one of us is applying certain amount of force and pulling it in a direction with a hope this big piece of furniture is going to move towards us. All right? So two people are pulling, and what is going to be the net effect of these two people pulling that furniture? So what we have to now do is to figure out a way to add the force. Add two forces actually, and this will be adding two vectors because forces are vectors and we want to add two forces. All right, so let's talk about how can we add two forces, or in other words, how can we add two vectors. Let's take a look at vector addition. So vector addition. As you know, a vector can be denoted simply something like this. Let's say I'm going to call this vector P. All right? Notice how I am writing it. Now let's say here is another vector Q. All right? And I want to add these two vectors. There are a couple of ways of doing this. One is a graphical approach. A graphical approach is basically based on making a sketch. to the scale. So you need proper drafting tools such as triangles, rulers, protractors, and a pencil. So assuming you have all that, let's do a graphical approach of adding two vectors. So given two vectors, what we want to do is to figure out a way to draw graphically the resultant of these two vectors. Remember, two people are pulling something. I am pulling it this way, someone else is pulling this way. These are all two force vectors. And this is going to have a net effect or a resultant vector somewhere in this direction along this way. But I do not know exactly what that is. And in order to do that, I am going to draw a simple graphical approach called parallelogram approach. In other words, I'm going to draw two parallel lines to these vectors. So what I do is I'm going to draw a line parallel to vector P from the head. This is the head of a vector, this is the tail of the vector. I'm going to draw a line parallel. Similarly, I'm going to draw a line parallel to vector Q from the head close. Okay, so this is parallel to this. This is parallel to that. Now, these two vectors, the lines intersect, and this point is where the resultant's head is, and the resultant's is going to look something like this. This is my resultant vector. So vector addition can be done graphically by using what I call as a parallelogram approach. And remember, in order to solve vector problems like this, you must draw them to scale. Once you have drawn to scale, you can measure the length of this vector and multiply your scaling value, and that would be the magnitude. In order to get the direction, assuming this is your horizontal line, you can measure this angle, and the resultant vector is R. So this is how you add vectors using parallelogram method by drawing parallel lines. Now, there is also another approach which is effectively the parallelogram approach, but sometimes people use a different word, triangle. And what does that mean? Well, basically you draw a triangle instead of a parallelogram, but you get the same answer. Here, a graphical approach. Here is a vector, horizontal. Here is a vector, P and Q. And in parallelogram law, we drew two parallel lines, and the intersection gave us the resultant. Now, using triangle law, all we are doing is, here is my original vector P, all right? Now, you can transfer this vector Q here, which is effectively drawing a parallel line again to that, and these two endpoints will give you the resultant. So effectively, parallelogram law or triangle law, both are effectively the same, but people use different terms. I want to make sure you understand they are effectively the same. You can use any word that you are comfortable with. So this is a graphical approach. Once you have found the resultant, you are going to express the answer using the magnitude and the direction. Please do not forget that. So you can measure these angles. All right. Now, graphical approach is very simple, easy to use. I encourage you to explore this. Having said that, it is also not very effective because you have to draw them to the scale, which means it is not going to be very accurate. So sometimes or often we would like to find out other ways of solving it. One way to solve that would be using an analytical approach. An analytical approach will involve formulas. Instead of just drawing to scale, you just make a sketch, use the information to calculate the information more accurately. So let's take a look at a different way of adding vectors. All right. Before we do that, I also want to make sure that you know how to subtract vectors graphically, because adding and subtracting are effectively the same operations. Instead of adding two vectors, you take another vector, add the negative of that, and that would be subtraction. If you're not clear, let me show you a very quick example. Vector subtraction. So again, let me draw the same example. In this case, we had vector P here. This is vector Q. P plus Q, vector P plus vector Q is your R. This is how we added vectors, and we found the resultant using parallelogram or triangle law, and this is your R. All right. Now, let's say we want to find out P minus R. How do we subtract? Well, P is your first vector. It's right here. Remember, my Q vector originally is like this. Now I need to subtract. So all I have to do is to reverse the direction. So instead of going this way, I'm going to come this way. This is my P now. This is my negative Q. All right? Because it is the negative direction. So P minus vector Q would give you your resultant. You see that? So this is the result of adding. This is the result of subtracting. So what we have done is we are adding the corresponding negative vector. Instead of adding Q, we are subtracting Q in this case. All right? So subtraction is pretty straightforward and easy, and I hope you understand that. And now let's take a quick look at multiplying a vector by a scalar. Now, I am using the word scalar. I'm not sure if I used it before. A scalar means it is just a number. We talked about the word magnitude, right? Scalar is just a magnitude. It does not have any direction. What are the examples of scalar? Well, area of a triangle. It doesn't have a direction. It is just a number. How many people live in California? It's a number. It doesn't have a direction. So anytime you use a number, your age, the population, area of a geometric figure, these are all magnitudes or scalars. So let's say we take a scalar such as 5 and multiply vector P. So this is my vector P originally, meaning it's a certain magnitude and direction. Now, if I multiply vector P by a scalar, it becomes 5P, and therefore, it will become 5 times longer. All right? So this is 5P. In other words, what has changed from here to here is not the direction, only the magnitude. So if you take a vector and multiply by a scalar, the vector changes its magnitude by those many times, but the direction remains the same. So multiplying a vector by a scalar is a very simple process. If your force vector was, say, 50 pounds, let's say here is a force vector, and this force vector is equal to 50 pounds at this direction along x-axis. Now if I say 5F, it will become 5 times larger like that. All right? Which means it is going to be 250 pounds in its magnitude. All right? I think it's pretty straightforward and simple. By the way, dividing a vector by a scalar will be multiplying by its reciprocal. So it's pretty much the same operation as multiplication, so I'm not going to spend time on that. All right? I hope you understand this. These are all simple approaches. Adding and subtraction, I have shown you a graphical approach. Now I would like to move on to an analytical approach with an example.